Sytecon staff here this week. I'm Marcus, and just a short introduction of myself as well. I've been at Sytecon for about 15 years, doing a lot of different things. Amongst them, I've been to Korea before, visiting, that was 10 years ago or something, but also been working with the development of the Opus suite for many years, and also supporting our customers, giving training courses, and make sure that our users get as much value as possible out of the tools that we provide. Okay, and I'm going to try to pick up the thread from where Oscar left off. I don't know if it's better with this one. Yeah, a bit shorter than Oscar, so maybe this is better. Yeah, I'll try it. Okay, so no, that's not. I changed my mind, sorry. There was too much bending forward. So, yeah, pick up the thread from where Oscar left off and talk about the integration of data for Ram-C and LCM analytics. I think the idea is to try to give you a picture of what do we mean when we talk about data in general. What kind of data are we talking about? How can we work with this data? How can we think about it? And ultimately use it for the purpose that we want, which is the analytics. And going back to this picture of the cornerstones, you've seen it a couple of times today. We'll see it again, but it's for keeping that thread so you know where we are. And I think that when we talk about data, it is what comes in here to build up the information. So this is really the building blocks. So and then there are many pieces of this puzzle, and where data, of course, is one of the main challenges. So, but we start from the beginning. So, what do we mean with data? And so I asked everybody's best friend these days, Mr. ChatGPT, and it said, well, data refers to distinct pieces of information. That makes sense. And it's usually formatted in a special way for analysis or processing. I think it was a pretty good answer because that's ultimately what we want to do. We want to use these pieces of information for performing analysis. So data can be in different formats, as you know. We talk about structured data, and then we mean things that are aligned in tables, databases, or spreadsheets in a way that we can apply. It can also be unstructured. Then we talk more about plans that we have, or unstructured text files, or an image, or a video of something. So, but that's kind of hard to extract something directly out of it. So it's unstructured. We can also think about data as something in between that are in XML formats or JSON files, and so on. Data can also be static, meaning that it's the same over time, it doesn't change. So things like product identifiers or part numbers are often, or stuff that is already printed and so on, they are fixed over time. But data can also be dynamic, meaning that it changes over time, which typically creates challenges in our branch. Such as prices for spare parts might fluctuate for different reasons. And again, we can be somewhere in between as well. We can have semi-static data, such as a design, description, or of a product or a system. But why do we need data? That might be obvious, but to give you some the mind view of it. So the data, it provides the foundation for making these decisions that Oscar talked about. If we want to make informed decisions, we need something to build those on. It helps us also to describe the systems that we're working with. And it enables evaluation of performance, just as we often want to do. Also used to ensure the compliance, by, there might be laws and regulations, stuff that we have to commit to, such as contracts or other fixed documents. And if we end up with another quote from our best friend here. So data is the foundation of all information, knowledge, and ultimately the decision making in various fields. So as in the Ram-C and Lsar. Okay, so if we just compare a little bit of a difference when we talk about data. Excuse me, I will keep you awake at least when I'm shouting in this one. So it can be data and information. So what is the difference? Well, data is typically the raw fact, the figures or the symbols or the observations that we've done. It may or may not have an inherent meaning or context. While the information is in some way processed, we have used the data to process and structure it in a meaningful way. And typically, the information is derived from the data through some kind of analysis or interpretation. So, to summarize, data is the raw material, while information is the meaningful interpretation or processing of that data. And if we use the life cycle here and look at life cycle and how data behaves, often when we look at modern, the type of systems that we are all working with, we look often at quite long lifetimes, long life cycles, especially if you are looking at like marine systems or stuff like that. It can be up to 50 years of a life cycle. And if you are in infrastructure business, you can talk about 100 years of a life cycle. And there will, during such a life cycle, happen a lot of things, both internally and externally in the world, that will affect how we can operate with our systems. And it also means that there will be many upgrades over a lifetime, meaning that we will constantly need updated new data. And it's not uncommon that a system that we are working with is built up from a set of subsystems. So we have contractors and sub-suppliers. And often we might reach an end of life for those components or products used in the main system. So that means that we have subsystems that has a shorter lifetime than the actual system that we want to operate. And if we look at softwares, we know that the lifetimes are even shorter. All right, and if we look in like large projects, as I said, we take an example with a naval platform here, and it's often about integrating other components and other subsystems. So the main task is to ensure the data quality and the data integrity. And of course, mapping the data so that it complies, and handle the change management, because, as I said, it will change over time. So, to summarize a little bit, so data is essential for decision making, and the data collection and processing and data management, that's a key in all large projects. And as I said, the life cycle of the system is typically longer than the ones of the products within the system. So, the summary is that we need to be in control of our data and the quality of our data. So that was like an introduction to what we mean when we talk about data. What is it? And the next step is how do we work with collection of data? How do we see this process and how do we go about it? And what we want to do in the end is to study this or shaping the availability, performance of the system. And as Oscar also mentioned before, there are different parts of this, of course. And typically we have a maintenance need from the system. There's a frequency for how often we need to maintain the system. There is a maintainability part of it, so how easy is it to access parts, what are the mean times to repair, replacement times, and all that kind of properties of the system as well. And then on the other hand, we have the response time from our support organization. There is something we need spare parts, and we need maintenance resources and facilities, etc., to be able to perform the maintenance. So this all comes with a cost, of course. So we cannot really decide on availability performance without keeping that cost in mind. And of course, last part is the operational requirements. We do have requirements or expectations on how we are going to operate with our systems. And the LSA work, the logistics support analysis, is about understanding the support requirements coming from the operations of the systems, while the support system design is about understanding how the support organization can answer to the support response that it gives, ultimately shaping that availability performance. So that's what we want to do. And for collecting data, there are a couple of steps here that I will go through. And first of all, so what data do we need, and what is the purpose of it? And these questions are important to ask yourself, so that you know the ambition on your work of collecting data. And then you need to know where you can find the data, and what are these data sources, where is the information available, how can I get it? And next step is to validate the integrity and to see if the data is complete, is it consistent, does it make sense? And I need to consolidate the data so that I'm only using the part of the data that is accurate for the analysis that I want to perform. I'll get back to what I mean in more detail. And finally, of course, we perform the analysis and get the answers. Oscar showed you this picture before, and I think it's a good analogy. So to start with, always when we talk about data collection, what do we need? If we are going to analyze the effect of a car crash on the human body, we do not need to know the color of his eyes. But we need to know the strength and the weight and the size of that. Well, so as Oscar said, and the same goes for any type of analysis that you want to do. When you build your model, you need to know what you are going to analyze so that you gather the data that you need. And if the idea is to analyze the capability of fulfilling a mission profile, then we need to know the overall system reliability, the overall support response time, detailed mission definition, etc. And for maintenance resource usages and bottlenecks, we want to do optimal spare parts allocations and cost driving repair tasks. So, but whether you're doing any of this, so if you, in the first case, the previous slide, it would be enough to just know the time between maintenance, the time to maintain, and the support response time. Then we can answer for the system level. But if we want to dig deeper and understand the reasons for downtime, or drill down to understand what are the drivers in terms of the support response time, we need also data on another level, on a deeper level. And of course, we can continue like this. Then we might want to know what specific part numbers that are causing downtime, etc. And you might want to know at what location and what operational sites and what type of missions are driving this. So the deeper we go, the need of data increases. So, some words on the data sources. Where can we find this information? Traditional way is what we often refer to as engineering estimates. So someone who worked with this type of systems before, they put the finger in there and they say, I think it's 5. And then we go for that. There are other ways. We can use parametric models for building from bottom up. We can also calculate values, of course, out of different activities. And of course, we might have a history. We might have been operating this system before for another usage or a similar system in a different environment and so on. So we might actually have experienced data as well. And yeah, in many cases, depending on the situation, we do, and depending on what type of organization you are working for, this information or this data might exist in-house or it might come from someone else. Typically, I mean, the reliability data comes from the manufacturer of a system, while the operational data comes from the operator. But again, depending on your need and the analysis you want to do, you need different type of data. And they can be stored, of course, as Oscar started talking about before as well, different ERP systems. We talk about LSA tools or homegrown solutions with Excel or text files or anything. So there are many different data sources, but the important part is to know where the data is stored to start with. And then, of course, we talk about different type of data that also can be stored in different sources. So logistics data that can be formatted, and again using the standards. We'll come back to that as well. Well, configuration data with a product breakdown and the versions of that, and we have transactional data such as number of repairs or number of demands that we've had, typically experience data, or it can be contractual data stipulated in a contract with the manufacturer or with the customer. So different sources, levels of sources of the data. But once we know where it is, we also need to understand the quality of the data and how it should be available. And we often hear wording like this, that we don't have any failure modes, or the part numbers are different between source A and B, and there's only history of spares demand, but there's no product breakdown structure, and so there are no links between maintenance tasks and failures. So this is about the integrity and integrality of the data. So how does it work together with each other? Does it make sense, and so on? So there's no idea of having information about how many failures there is if we don't have a part number for that part. So it's all connected, and that's important to have control of as well. And so if the sphere of data is often bigger than the part that is useful, and useful here, of course, I refer to the analytics that we want to perform. What data is it that actually is useful for the purpose that we are looking at? And of course, there can be, Oscar mentioned as well, you can work with different types of ETL, extract, transform, and load tools to gather the useful data out of the total data. And here's a good example of what I mean with integrality, that if you have a breakdown that should comply to what failures you have, you should have failures for the part that you have in your breakdown, not for anything else. And the same with spares demands. You should have maintenance tasks that represents the failures that might happen, and accordingly the resources needed to perform the maintenance. So often when working with models like this, you need integrity in the data so that you have unique identifiers that matches between, so that it's possible to follow and use this data in a meaningful way. Okay, we're getting close to the end here, but so consolidating the data. So it might be that for our analysis, at this point in time, we might only be interested in the first two subsystems. So then we don't have to gather information about the other two. Maybe we're only interested in maintenance performed at a certain level because that's what concerns us at the moment, something else. The rest of the maintenance might be contracted to someone else or at a different level. And the same thing when it comes to spare parts. Maybe if we're going to provide an initial spare part list, maybe we should focus on the stuff that matters. Maybe we should draw a line somewhere and say that we're only looking at spares $100, for example. And also, again, if we have a set of analysis that we're going to perform, might be that we are not looking at preventive maintenance at this point of time. So we don't have to go into the details of that. Same thing, maybe we're not interested in consumables at this moment, so we shouldn't look for that data either. All right, so now we've collected all the data, we've gathered and structured it, and we can feed the models that we want to build, and we are ready to perform the analysis. And of course, it's important also to remember that the results that we get out, once we have collected our data, we should always keep in mind the understanding of the relation between the outcome and the input. So if we have limited the scope to a subset of the information or the data, we should also be aware of that the result is limited to the same subset of data. Okay, this picture has been shown before today, and I think it summarizes what we are trying to do with Opus in a good way. So going from the data that we talked about now, all the way to the decisions that we ultimately want to provide. And now I'll focus on this first part, the data part and the model part, and talk a bit about how one of the later additions to the Opus suite, which is Connect, can help us in this matter. Because it's also interesting, I mean, our experience has been that if we look at how much time our customers spend in those different boxes or phases and so on. So, I mean, it turns out pretty quick that a lot of the time is spent over here, gathering data, understanding the data. That, I mean, we want to spend time over here to get understanding and insight, so we can do this. If this goes quick, we can do this much more often. And that's great, because then we can provide even more decision support, and we can do even more analytics. But if we get stuck here, it's kind of boring and it doesn't pay off so well. So if we can make this quicker, we will get more decision support at the end. And that's really what's been driving the development of this tool, Opus Suite Connect, which is an application for data ingestion. I mean, that means pushing the data into the model and integrate it further so that we can use it in Opus Suite, and also convert it to this Opus Suite format that we are looking for. As of today, we support the standards S3011 for specifications and GEIA 007, but also as a customized projects, we can adapt to other formats that might be in use at the customer's sites. And it's about, as I said, loading, merging, and exporting the resulting Opus Suite model. So what are the main benefits with a tool like this? Well, first of all, we can increase the efficiency in building and maintaining the models. And that's what I said in that big red arrow before as well. That I think that's the main benefit, that we actually becomes more efficient in this entire process so that we can provide more analytics, more decision support in the end. We also reduce the risk of manually introduced errors. So, I mean, sitting in Excel sheets that are thousands and thousands of rows, it's easy to somewhere do a manual error. If we can create an automatic process that's doing this for us repetitively, the same way, time after time, it will be more secure. And also, with a tool like this, we can leverage on the synergies from integrating data sources. Just as I said, having a lot of benefits from this type of automized process. And the main functions of the tool is that we can ultimately generate that Opus Suite model from an Lsar, for example. And we can also aggregate data from multiple sources. I'll show you an example of that, what I mean. But that's also a pretty nice, neat function that we can do. And of course, we can also do these quality and consistency checks of the LSA data. And if we apply this, and this is again, pick up the thread where Oscar left off, you were probably, it was very exciting there, but in the end over there, we want to do that Opus 10 and Simbox analysis. We want to be able to build that model. And we come from here somewhere where we have the data. And then we have, over here we have Opus Suite Connect. So we have, from the standard formats or others here, we can import the data, validate, filter and aggregate, and then we can produce a file that can be directly imported into the Opus Suite. So the big question is, how can we go from here to here? Well, if we have data in the LSA tools, they often have export functionalities into those standards. So if we have data structured in a good way here, according to the standards, it's a one-click wonder here. But that might not be the case. So then we have some different other options. Oscar mentioned this as well, but either we can go, if we have other sources, we might go through some other ETL tools, or we can customize and build what we call pre-converters that forms this data. Whatever structure it has here, we can actually form it into the specification formats so that we can run it again. So here's an example on how we can work with merging data. As I said, often it's not unusual that you work with large projects that consists of many subsystems and many sub-suppliers. So here's an example. Let's say that we have a partner that we call it contractor A, and they're providing us with a subsystem A. And the data comes in the S3000 format. And we, as the system provider here, we use Opus Suite Connect, and we're building a full system model. So what we can do is to, when we get that S3000 data, we merge it into Connect and put it into the full system model. Next, we have another contractor that we call B, and they are delivering the subsystem B. And they are exporting their data in a format from the GIA standard. But with Opus Suite Connect, we can take that and merge it in directly, even though it's a different format. So this is what merge functionality does in Connect. And it adds on to the same full system model there that we are looking for. And the last example, we might have a third contractor that actually also works with Opus Suite. So they are providing us with input files ready for the Opus Suite. And what's nice here is that we, again, can just take it in, merge it into our full system model, and ultimately get out a complete model for all the three sub-suppliers, even though they provide us with data in different formats. So again, it's about streamlining and making this process more efficient. Okay, so talking a lot about data models, and what do we mean when we talk about a data model, and why do we need one? So a few words on that. So what we want to do and what we're talking about all the time here is to perform this Ram-C or LCM analysis, and we want to provide those nice graphs and visualizations and so on. So that's great, but to do that, of course, we've talked a lot about the data. We need that data. And it's great, we can structure it into the specification formats and so on. But to be able for us as a software provider to perform this analysis and build a tool, a software that can handle any type of problem and any scenarios, we need to work with a structured format that we make the Opus applications understand what data means what, right? So we need to build a model that forms the data and structures the data in a way that the software can understand. And as the years goes, and we try to make also this data model as close to the standards that our customers are working with as possible. So what we've done during the last 4 or 5 years also is to coming much closer to these S-series. We talk about product breakdowns that looks very much like the logistic control numbers of an Lsar. We talk about items, which is very much like the hardwares or part numbers that we have in the S-series as well. So the same with failure modes and maintenance tasks and so on. So we're trying to form that data model as close as possible to the standard so that it becomes easier to integrate. And that's also actually what made it possible for us to build OPUSuite Connect, this modernized data model that we have with OPUSuite today. But anyway, so that's necessary. And so how do we represent these data models? Well, there are different ways of representing the data that we are using. And for the ones of you who already uses OPUSuite, you will recognize this as one of the input tables. But so that's a table representation of this, a part of this data model that we're talking about. So we're looking at it, it's stored in input file, it's stored, which is structured in a set of input tables, which has a name. In this case, it's called item, but I mean the table name is item, and it has different type of columns. Here we have an identifier column, typically can be the name of the part or part numbers or whatever it is. We also have different type of data sets for this list of identifiers, and here we're looking at spare part prices. Can also be other additional data that is needed for the analysis that we are performing, as well as other documentation of data at the end over there. So that's one way of representing the data. And it has, of course, it has different data rows. Each data row consists of data in this structure. Another way of representing this data once we've put it into the tool is with a graphic representation. It can look something like this. Here we have a structure showing the product breakdown, showing all these breakdown elements or logistic control numbers, whatever you're using type of terms, and as well as a support organization showing us the different maintenance locations and operational sites, etc. We can also, if we're working with redundancies, we can build functional block diagrams, looking something like this as an example. So this is another type of representation of this data that we have. And a third one can be, again, this is the JSON representation of this item table from the Opus input. So that's another way that we can represent this data model of ours that we can integrate and work against. So if we take a quick tour here around the data model of OPUSuite to look at what data is it that we actually need and the basics of a very basic model. And first I'm going to describe the model and then I'll go through what data we need. So first of all, we want to perform some kind of operations. It might be we want to fly with an aircraft or helicopter, we might want to sail with a ship or drive a train or whatever it is, but if we want to ultimately perform some kind of operations. To do that, we need a product. The product is which is the description of a system or a family of systems or what it might be that you're looking at. And of course, with all its, with the breakdown of that system, with all the parts of such a system. We also need to describe where we operate with those systems that are defined by the parts. So we need to model an organization showing where are the systems in operation and also where can they be maintained, where do we store the spare parts, etc., etc. So that builds up an organization with the actual locations. And of course, when we start to operate with the systems, things will happen. They will fail, will break, they will need. We use the concept of events, and events can be random, so unforeseen failures. They can also be planned events according to a maintenance schedule. But what's common with all the events is that the system becomes inoperable. We have to stop with the system and do something with the system before we can go out sailing or flying or whatever we're going to do. So we need to perform some kind of maintenance. This maintenance often leads to a replacement of one of the parts in the product. And we also need to describe the capability of performing the maintenance. So where in our organization can we perform these tasks? And that's really the basics of the Opus Suite model. Pretty simple, maybe. Anyway, so if we go through what we need here step by step in terms of data, because this is more of a structure. So to describe the organization, we need to name the locations in this support organization. So we have operational site A and B, we have maintenance location A, B, C, etc. And we relate them to each other according to a structure, and we can define the expected transportation times and so on. And of course, there are again a lot of additional data, but this is the basics that you need. When it comes to the products, you name the components of your product and relate them to each other again. It can be a flat structure, everything below a top level, or it can be any detailed level as you wish. And for the spares optimization, we also need to define the prices for each component. When it comes to the events, you don't need any events actually, but then it's not so interesting. If nothing happens to the system, you will have 100% availability, and it's not much of an analysis. But in real life, there will be failures, so we need to give failure rates or mean time between failures, which is, the difference that it's 1 divided with NTDF is the failure rate. So, and it can also be, as I said, scheduled or fixed intervals for maintenance. And once we perform the maintenance, we need to replace components. So what parts do we need to remove from the system and maintain? And then we also need to define how we rectify or repair the components. And for the capabilities, simply defining where this maintenance can be performed. And lastly, of course, we name the products as operating systems, and we define how many we have. We have 5 helicopters or 10 aircrafts, or what it is, and the expected operating hours per year. So that's the basics of what we need for building the first Opus Suite model. Okay, so I'll continue with this as a background here, and especially the data handling. I'll give you a use case, something that we've been working on for the last year approximately, which is a very big industrial project in Germany, where the German Navy have bought frigates from a shipyard in the Netherlands, which is called Damen Naval. So I'm gonna. This is really interesting because it's really an integration project from the real world. So that's why I think it fits well with this presentation about data and integration and Opus Suite Connect. So anyway, F126, it's a frigate, so it's a pretty big ship sailing in the Nordic Sea mainly. And in 2020, so a few years ago, the Damen Naval shipyard, as I mentioned, they were awarded the contract by the German Armed Forces. And they started the construction last year, and the plan is to sail the first ships in 3 years. And the original order was for 4 ships and eventually another 2. And this is, as I said, it's the largest, so it's a big ship, so yeah. And we, Sytecon, both our German company as well as colleagues from Sweden, have been working as a consultants in this project, and we are also providing softwares for this project. And as a reference, yeah, it is a big ship, so I don't have to say more about that. But the main question here, as I said, the main purpose of this presentation is to talk about the integration that was done. So then it's important to talk about why are they even working with this integration towards Opus Suite. And for Damen Naval, there are both internal reasons as well as external reasons for doing this. And internal ones is that, well, they are working with a large ship, and it is really about, putting a lot of subsystems together. So this ship is consists of over 100 of different subsystems from different suppliers. You know, weapon systems, radars, communications. So performing the ILS or IPS work for this frigate is about handling or managing data from just as many suppliers. So that's a challenge. And they want the ability to do life cycle optimization, to find cost drivers and availability bottlenecks and so on, in order to improve, of course, the system that they're building. And they also want to provide the spares recommendations, and they need to do this both to ensure a certain level of system availability, both under their sort of peacetime normal conditions, as well as how prepared they can be for crisis and any other type of situations where they need to sail abroad and so on with this ship, so that they get limited support or any type of endurance type of problems and so on. And lastly, they also have to ensure that they don't need more people on deck than the actual crew size limits of the ship, because there are limitations on how many humans you can have on board. So if we build a maintenance solution that needs twice as many people, it's simply not working. So that's the internal reasons, and as goes for the external factors for integration. So the BindPW, which is the German defense acquisition organization, they requires that Damen monitors the overall life cycle cost during both the construction phase as well as the delivery of these systems. It also requires Damen to file a life cycle cost report to the ministry twice every year. And also have an LCC model ready available to be able to make future product decisions based on LCC analysis. And as you see, the customer here, the German Armed Forces, they are really focused on life cycle cost. They want to make sure that all decisions, both during the construction and the delivery and the usage of this ship, is based on smart decisions, based on the fact that it will live for 50 years. So we need to understand the impact of the costs for the 50 years to come. And so a quote here, shipbuilding is system integration, and then that means that ILS in shipbuilding is too, and it's simply too much data and information for any type of manual data management here. So what did we do as a software and consultancy company to try and help them with this? Well, we made sure that they can integrate the Opus suite through using the Connect application in the data management process. And with Connect, they can create the subsystem Opus suite models from the supplier data and then merge those into one large system model in an overall system ship model. They can also update existing models from actual Lsar data, so they always stay with the latest available data, and as well keep the traceability of model updates. So this is a really complex picture again, but we're going to focus on two parts of this. And first of all, it's the top there. In this data management process that they created for this project, they decided to create a data collecting tool. And the purpose of the data collecting tool is to gather information from all the sub-suppliers in one and the same format. So they force all their sub-suppliers to file their data into this data collecting tool on a specific format. And the second part here that is interesting is that with this data, they use what they call a CDP, which is a common data pool. The common data pool is storage of all this data, and based on different formats, among them the S series as well. And the best part of this for us then is that once they have all the data, the common data pool on the S series format, we can use Connect to directly integrate with Opus 10 and also do lifecycle cost analysis with Catalog as well. So what we can say is that they have have industrialized and increased the automation in the LCC process. So as I started with, the maybe most important part with Connect is that it helps them to continuously and rapidly perform new analytics to provide answers in a timely manner. And today this is used because it maintains and updates this overall model. And with this model, which is pretty nice with the cost analysis part of Opus Suite, is that we can also transfer the costs to the German armed forces cost structure. So they have their own way of defining the cost structure. How do they want to break down the life cycle costs for their ship? And with Opus Suite, we can do that. We can implement their cost model, and then they get the types of graph that they really want to see. Okay. And also, Oscar also talked about system design report as one of as important activities within the series and so on. And the results from the analysis from Opus Suite can contribute in these reports to understand failure frequencies, etc. And we can also file these LCC reports to the customer every 6 months as expected. So that was a I think pretty good example on how we applied integration of data with Opus Suite for our customers. And finally, the last part of this presentation, I'll talk about very short about the Opus Suite as maybe artificial intelligence suite. So a few words on that. It's hard to not do that these days. But if we just take a short recap of the Opus Suite journey so far, what we've been doing. So we have been based on mathematical models. That's what we've been relying on for those 50 years. And it's been successful in very many ways. During the last 20 to 30 years, we've also added Monte Carlo simulations, where we use randomness rather than analytic approaches to solve deterministic problems. And over the years, we've also increased use of heuristic optimizations, and heuristic means smart ways of iterating us forward to new solutions. It has given us new functionalities in the suite over the years. For example, the level of repair analysis functionality in Opus 10, as well as the solution finder, etc. I might show you more about this the upcoming days as well. And the last addition to the suite is the Opus Pbl software that I will talk more about in the afternoon. Not right now, because we need a break, I think. But anyway, but if we look into the future, we see that we also need to adapt to the AI revolution that we're in, and how we can use machine learning and generative AI to also support the use of Opus Suite. But where? Well, basically and theoretically, we could use AI in any part of the process of any analytical software, from extracting data, transforming data, represent the models, forecasting, enhance and optimize, and then give the insights. But where we are working right now is this area. We're doing some internal researches. You can say that Evo functionality is a way of AI, and we'll come back to that. But we're also looking at ways of understanding how we can use generative AI for transforming unstructured data maybe into a format automatically as well. But we're working on it, so stay tuned for next year. And just a map of how it could work with customizing some kind of understanding for generatively learning how to interpret data in order to create finally the Opus Suite models that we want. So if we summarize this entire presentation, there are, as a fact, different challenges when it comes to data. For example, we have many data sources, we have many suppliers, and we have data in different formats. Remember that it's important to use the right data, the data that we need for the analysis that we're going to do, and the quality is important, but also expensive because it takes time to keep it complete and keep the integrity of the data, etc. But with a data collection tool and a common data pool, together with integration to the Opus Suite, we get a solution that can deal with many sources and data formats, and we can ensure quality and that the right data is used. So the key sort of takeaway message here is that data management can be a challenge, but if you use a structured and proactive approach, you'll be fine. Right, thank you. So I understand that was a lot to take in and listen to, and now it's, I think, Mr. Young will tell you, but I think it's time for a break. But if you have any questions now, during the break, after the break, or at any time, we are more than happy with Oscar and I to have a conversation.
혹시 뭐 질문 있으세요?
이게 좀 물리죠? 이건 더 물리나요? 똑같아요? 비슷해요? 요약을 제 맘대로 할게요. 마커스의 의도와 관계없이. 아까 데이터라는 게 뭐였었죠? GPT가 답을 이렇게 했습니다. 인포메이션 덩어리다. 그것까지는 아까 얘기했었죠. 그 다음에 어떤 성질을 가져야 되느냐, 분석을 할 수 있고 프로세스가 될 수 있어야 된다, 이렇게 정의한 것 같아요. 우리 요 데이터 얘기를 지금까지 했습니다. 앞으로 이제 데이터 얘기가 안 나올 텐데, 데이터가 왜 중요할까? 그 다음에 데이터는 왜 이런 식이 꼭 되어야 될까? 그 다음에 우리가 관심 있고 지금 우리가 하고자 하는 게 이제 군수 쪽이잖아요. LSA를 하거나 뭘 하건 간에 어쨌든 우리는 데이터가 필요한데 여기에 단순한 인포메이션 덩어리가 돼야 되는가? 이런 질문이 일단 있었고요. 두 번째, 그게 만약에 성립이 된다면 어떤 형태를 또 가져야 되는가? 이제 이런 문제가 있었고, 그렇다면 우리 군수에서는 이런 식의 데이터 형태를 갖는 게 중요하다라는 게 이제 마커스의 얘기고요. 그게 이제 나와 있던 게 S 시리즈 이런 형태로 포매팅이 되어야 된다는 얘기죠. 그 사례를 이제 든 게 여기 프리깃이라는 게 호위함인가요? 제가 잘 몰라서 그런데 독일의 호위함 프로젝트 하는 과정에 사실 저도 참관을 갔었습니다. 제일 문제가 뭐냐면 데이터는 많은데 우리나라도 똑같을 것 같아요. 이 데이터를 분석을 위해서 어떤 형태로 포맷을 가져야 되느냐 이런 문제가 사실 저 때도 있었습니다. 그래가지고 S 시리즈도 물론 그 당시에도 있었고 독일 나름대로 자기네들도 군수 관련된 정보 체계가 있었는데 이런 것들을 어떤 형태를 또 어떤 포맷을 가져야 되고 어떤 구조를 가져야 되는가 이거에 대해서 왜 고민을 했냐면 잘 아시겠지만 우리는 분석을 합니다. 분석한 다음에 우리는 항상 그거에 대해서 이해를 하려고 해요. 왜 이런 결과가 나왔지? 그러려면 다시 빽 이렇게 됩니다. 뒤로 가야 돼요. 뭐가 문제가 돼서 이렇게 결과가 나왔지? 이게 돼야 되는데 이게 돼야지 데이터입니다. 이게 안 되면 데이터가 아니에요. 근데 여러분 잘 아시지만 요즘에 AI나 머신러닝 머신러닝이 통계적인 기법까지 포함한 머신러닝 그 다음에 더 들어가서 딥러닝 이런 것까지 얘기를 하고 있습니다. AI의 가장 큰 단점이 뭔지 혹시 들어보셨어요? 뭐라고 생각하세요? 무지하게 답을 잘 내줘요. 진짜로 해보면. 근데 문제는 뭐냐면 왜 그러지? 이걸 모릅니다. 심각한 문제예요. 근데 우리 군수 분석을 하면서 AI처럼 답은 잘 내주는데 스페어 몇 개. 근데 왜 이렇게 나오지? 이거 설명 못한다 그러면 말이 돼야 돼. 그러면 의미가 없는 거예요. 우리가 왜 코스트를 분석을 해야 되고 다른 것들, 이런 것들 분석을 해야 되지? 이런 거에 대해서 답을 줘야 되는데 답을 못 준다는 얘기입니다. 그래서 뭐 지금 빅데이터도 나오고 뭐 AI도 나오고 하지만 이런 데이터들은 일단 제껴두고 우리가 어떤 데이터들을 정형화해서 모았을 때 그 결과 가지고 분석을 하고 그 다음에 결과가 나왔을 때 해석을 해야 되고 이게 삼위일체가 돼서 인과관계를 이해할 수 있어야 되는데 그렇지 못한 데이터 구조는 의미가 없다는 뜻입니다. 우리 군수 분석에서는 그런 차원에서 지금 마커스가 얘기한 건데 마커스가 너무 많은 자료를 짧은 시간 안에 막 얘기하다 보니까 한 곳에 집중이 좀 안 돼가지고 얘기할 수도 있습니다. 어쨌든 이따 뭐 질문을 따로 하셔도 되고요. 그 원래 의도했던 내용은 제가 지금 말씀드린